Konnichiwa friends, my name is SMS Masi and welcome to part 1 of the music audio multiclass classification bootcamp. Okay, so in this video we are going to make a deep learning model that correctly classifies the category of the musical instrument played. Okay, so this video is all about how we solve the problem for our audio multiclass classification, how Librosa work, what are the pre-processing steps, and how basically we understand audio features in a deep learning training. Okay, so for our next video we will learn how to load the dataset, make it to data loader, and how to use GPU in the data loader. Okay, so in this video the main problem is to correctly classify the song genre here. Okay, so we have this data set named Citizen and we have here 10 genre. Okay, so like blues, classicals, hip hop, etc. we are given, and for each genre we are given 100 songs. Okay, like for jazz, metal, pop, reggae, rock, and each genre have here 100 songs which we could train on. So the whole point of our deep learning model is that we are given 10 class genre here, and we have to predict with our deep learning model out of the one of the 10 genre. Okay, so we will be making 3 deep learning model that clearly classify music based on the audio. So now the domain of the problem. This is a supervised machine learning problem. Okay, so we are given an label correct train data here. Okay, and we have to predict the unseen data here. The category here is that it is a multi-class classification, as we have to predict 10 labels. Okay, then for our metrics we are using our F1 score. Okay, and for the domain of the project is audio classification. Okay, so our goal is to make here 3 models: the CNN, the LSTM, and the pre-trained model. The CNN model is fast, simple, and strong for performance model used in computer vision. Okay, this is one of the basic model for our audio problem. Then we have the LSTM with captures time dependency. It is mainly used for capturing rhythm well and is for sequential learning. And then we finally have our pre-trained model, which is basically using transformer from the Hugging Face. Okay, it will be give best accuracy and is helpful in real world deployment. Okay, so in short we are making 3 models here. Now the packages you should learn. Okay, so for this project you need to learn at least 4 packages here. Okay, so it's 4 packages. Okay, one is your PyTorch, then Pandas, then NumPy, and then finally Librosa. Okay, this Librosa is a Python library that basically converts raw audio sign into meaningful features. Okay, I mean this is one of the library that is the same as Pandas for the CSV file. Okay, this Librosa file work as Pandas for the audio files here, and it basically converts raw sound into meaningful features. Okay, so here in our Librosa you need to understand 3 points here. First is how we install and import packages. Okay, and how we load an audio file, and how we extract the feature. So we install using our pip install Librosa, and then we import using import Librosa. Okay, so we can now use one song feature using audio SR equals to Librosa dot load, and here we have to paste the audio link here. Okay, so we run it, and then we pass the audio file path, and then we load the audio file here. Okay, and then we extract feature using mail equals to Librosa dot feature dot spectrogram here. Okay, and inside it y equals to audio and sample rate equals to SR. Okay, so here basically how we load: first install, and then we import, and then we load the audio file, and then which gives us an audio and a sample rate, and then the Librosa dot feature which give us this mail spectrogram. Okay, where we pass the audio and the sample rate given. Now your question may be, what is this audio here? Okay, so it is a one dimensional NumPy array of sound samples. Okay, Here each value represent the amplitude of the sound wave at a specific time. Okay, so 0.02, 0.01, minus 0.02 basically determines the amplitude on the 1 second, 2 second or 3rd second. Okay, it gives us in a one dimensional numpy array, and for 1 second, 2 second, 3 second to the last audio length, okay, it gives us the amplitude at that particular moment. Okay, this is useful for generating the male spectrogram here. Okay, and then after the Librosa feature basically gives us what feature we want to extract. Okay, so if you want to extract male spectrogram, we write here male spectrogram here. Okay, and we pass the audio and SR which we got from the above file. Okay, so with this the install, load the audio file and extract feature is the three main thing you must understand to do this project. Okay, you don't need to learn anything else except the three things I showed you. Okay, how to install, how to load the audio file, and how to extract the feature is the only thing required. Now we come to the audience basics. Okay, and first thing you must know is that what is sampling rate. Okay, so basically it signifies the number of samples captured per second. In short, basically for 1 second how many samples are you recording. Okay, if it is a higher sample rate, then you will get more details in frequency. Okay, so all musical instruments have rich harmonics, so basically they have very high sample rate. Okay, so for example our speech have 60 kilohertz sample rate, but for music we have 22 kilohertz sample rate. Okay, in average. So if you will be printing the SR here which we got from Librosa load, you will get here 2050. Okay, which is the by default sample rate for Librosa, and it is the number of samples captured per second. Okay, if it is too low, you lose important tonal information or the instrument may sound similar to the model. Okay, so a high sample rate for musical instrument is a plus. Then we go to your mono versus stereo. Okay, so here mono means the sound is coming from one channel and stereo means sound is coming from two channels. Okay, here like if you have used headphones, then you must have known that for some songs you hear the audio from the left and right, so basically you understand which is left and which is right, and for some audio you hear only one channel, so it doesn't depend on whether you put the headphone in left or right. Okay, now comes the bit depth. So here the bit depth basically represent the quality of the spectrogram here. Okay, the image which is formed. Okay, so if it is like 8 bit, then we get low quality, and 24 bit then studio quality. Okay, it basically controls the dynamic range. Okay, quiet versus loud sound, and it is important for music genre detection. Okay, now the other important audio terms are amplitude, which basically height or strength of a sound wave, the frequency which shows number of vibration per second, then pitch which is directly correlate to amplitude, then loudness which perceive intensity, and finally duration which is basically shows the length of time of a sound last. Okay, so this is an important term which you learn in class 9 to 12 of your science subject. Okay, so you understand this sampling rate, the mono versus stereo. Then now comes the time domain versus frequency domain. Okay, so the time domain basically shows the waveform over time. Okay, so this is a time domain graph where we basically see the waveform of an audio file here. Okay, so here in x-axis we have here amplitude here. Okay, and in y-axis we have time here, and in time domain we could see the waveform of the audio. Okay, but for our CNN we generally use our frequency domain. Okay, so this is a spectrogram which basically shows the frequency present in the sound. Okay, and it is obtained using Fourier transform. So here in x-axis we have frequency which we get from Fourier transform, and y-axis we have time here. Okay, so why it matters in music? So the music is defined by notes, harmonics, timbre. Okay, so the images of audio like spectrogram and male spectrogram basically help better understanding of CNN, not the time domain graph. Okay, this spectrogram or the male spectrogram basically shows the more feature and frequency which help determines the music of the audio file here. Okay, So now comes the audio pre-processing part, where basically we understand what are we doing. Okay, so the computer cannot listen, they could only see. Okay, it is a very fact that computer don't have ears like us. Okay, but they could see by using the help of CNNs here. So they are practically aren't listening to the audio, they are actually seeing the spectrogram images we gave them. Okay, so they learn audio features like amplitude, frequency, etc. Okay, which are given in spectrogram or the mail spectrogram or whatever Librosa feature you will be going to use. Okay, so here the raw audio is rarely fed directly into neural networks. It is always sent through audio features and never directly. Okay, so now how basically it learns the audio features. Okay, it is the same way we learns the boy and girls by pitch, loudness and emotions. Okay, so basically when we hear and singing voice, we basically learn the pitch, loudness and emotion, and we basically understand that the singer was in male or female. Okay, it is the same way the computer will not listen to the audio but understand and sees the audio patterns of boy versus girl singings. Okay, like we human do, and it will classify. Now for the pre-processing part, so generally we could do these common pre-processing steps. Okay, first is resampling, basically converting everything to fixed sample rate here. Okay, so basically we do it by librosa.load, and here after the audio file we pass the sample rate we want. Okay, so in this way we are here forcing the sample rate for all audio files here. Okay, this is one of the important step you could take. Okay, so here we pass this sample rate explicitly and it will force the audio. Okay, then come the trimming silence here. Okay, so whatever the audio is there, and there is always a silent part at the end and at the start here. Okay, so basically by using streaming silence, we basically are removing the audio samples that are not required. Okay, it will basically trim the first and the last silent part here using librosa.effects.trim here. Okay, now comes the normalization, where basically we make all audio have similar loudness here. Okay, so when we do librosa.util.normalize here, we basically are normalizing the loudness of the audio file. So here in first the audio we are passing it to trimming and the normalization here, and then we could also do here padding, where basically we ensure all audio files have fixed length. Okay, so we multiply the max length by sample rate here and we get the max length here, and if the length of the audio is less than the max length here, we basically use np.padding to get the audio file from 0 to that much length. But if the length is more than max length here, we trim the audio files here from first to the max length here. Okay, which is basically 3 seconds here. So basically it will go from 0 to 3 seconds here for the audio part here. Now we are going to Librosa features, where basically we will learn what are the features we could take apart from the mail spectrogram here. Okay, so if you will go here, you will see that I am using mail spectrogram here, which is generally more common for our musical classification and audio classification. So we call it by librosa.feature, and then we pass one of the feature which is required here. Okay, so we have like mail spectrogram, MFCC, chroma strip, spectral centroid and zero centroid. Okay, so we could also combine them too. So here basically instead of mail spectrogram we could also write MFCC and you could run it. Okay, and you could then see the spectrogram image. So wait, let me write it, just a second. So here the spectrogram here I am showing it to you using import librosa.display here, and here basically I import the numpy and pplot to show you this spectrogram here. Okay, so the first audio file which is blues here, and this is the whole spectrogram image of that audio here. Okay, this is the spectrogram image your model will learn. Okay, you could change here, you could paste here, and you could also use here MFCC. Okay, so if you will be using MFCC here, you could see the spectrogram which the model will learn. Okay, it is generally used for speech recognition, and it basically captures the timbre or harmonic, and is generally used for identifying the person here. Okay, so here each ups and downs here defines the timbre here. Okay, next come the chroma STFT. So we write here chroma STFT, which is generally used for music notes classification. Okay, so here basically we represent the 12 notes C sharp, C, A, etc. using this colorful image. Okay, and it's generally used for notes classification. Then we also have spectral centroid and the zero crossing rate. Okay, which you could use and experiment for this project too. Okay, and also you could combine them too, so your model is learning many types of spectrogram images. Okay, here basically Librosa.feature converts raw audio into time frequency representation. Okay, so we have here y-axis, we have time here, and in x-axis we have frequency here on male scale, and here basically the colorful ups and downs here shows the amplitude rate here. Okay, energy at each frequency, or basically the amplitude here, and this is the thing basically the model will learn. Okay, now comes the next question is that how Librosa feature could find the musical category. Okay, so if you'll see the three graph clearly, here you will see one violin, one cello, and oboe here. Okay, so you could clearly see the difference of the male spectrogram images for three musical instrument here. Okay, so here the violin have, and particular male spectrogram the cello, and then the oboe here. Okay, so here this is basically what the model will learn and categorize the musical instrument by seeing their spectrogram images. Okay, so you will see there that oboe have a very different spectrogram image than the violin and the cello here. Okay, so here by this learning the whole our project will work here. Okay, so each musical category differs by musical notes. Okay, so for example one genre like here blues or country or disco have your high guitars here. Okay, so by seeing the guitar spectrogram here, the model will clearly say that it's an country image or the hip hop image. Okay, so this will help us identify the musical genre category here. Okay, so finally the whole summary of this video is to how to first import the Librosa here, which we do by pip install Librosa. Then we import Librosa file, and then we load the Librosa file which gave us the audio and the sample rate here. So we get the file path, and here we pass the audio path here, and it will give us the audio here and the sample rate here. Okay, here you must understand that here the audio is not an image, but it is a one-dimensional array of number. Okay, it basically represents these sound waves. Here basically 0.01, 0.02 etc. number basically shows the per second here. Okay, so if you will print the audio here, you will see that it's an numpy array of numbers here. Okay, and it basically signifies what was the amplitude at that particular time. Okay, in short the millisecond here. So here the audio is an numpy array. Okay, not an image here, and basically not for training here especially. Okay, now the next come is the male equals to Librosa.feature, where we pass the feature which we want. Okay, if you are passing the male spectrogram, we are getting this spectrogram 2D matrix here. Okay, also this is not an image yet, but it can be visualized as one. It's a two-dimensional matrix here, which basically the frequency shows the frequency bands basically from low to high, and the columns here defines the time frames. Okay, so basically in short, the XY graph where basically our columns is the time frame and X is the frequency band here, frequency band here. Okay, so here if we will be printing this mail here in our bottom, you will see that it's an two-dimensional matrix here. Okay, here the rows define the frequency band and the columns the time series, and here each value represent the energy at each frequency and time here. Okay, so basically energy at particular frequency and time here for our mail spectrogram. Okay, now the next thing we could do is that we do Librosa.power to decibel. Okay, basically this converts the values into decibel. So now you may ask why decibel. So because human hearing is logarithmic, okay, not linear, so we perceive the audio in logarithmic scale here. Okay, so here the row values in male are large and uneven. Okay, so if you will see here, you could see that very large values here. Okay, so we have here E here, which is an Euler constant, which basically shows it's a very high value here. Okay, so basically what we do is that we use Librosa dot power to decibel, and then we pass the male here, and then we print the male decibel here. So here you will see the large values are normalized into small values here. Okay, so you will see that we could now and the two-dimensional matrix here. Okay, so this is basically what it do. Okay, so let's also print the male decibel here, and you will see that it shows the normalized spectrogram here. Okay, so this is now the spectrogram the model will learn. Okay, so this is a male decibel spectrogram which an human will perceive. Okay, and it is a normalized spectrogram here, and this is basically what we will be passing to the model here. Okay, it is in scale normalized value. So it's male the picture, so technically we could say that it's just a numbers in a 2D array. Okay, so you will see that it's an 2D array here, not actually in picture, but the model practically will treat it like an image. Okay, so the model will actually be treating like an image only for this two-dimensional array. Okay, and it will be passed to the CNN, and it will do the prediction here. So this was the whole concept for our audio classification task. Okay, so that's all for today, and thank you. So this video is all about how we solve the audio classification problem using Librosa, how we could pre-process, and how we convert audio features to our spectrogram images so our model will learn. So in our next video we will learn how to load dataset, make it to data logger, and use GPU. Okay, so that's all for today. Thank you and bye bye.